In previous tutorials, we've talked about the physical layer, we've talked about hubs. In this tutorial, we're going to look at the switch and how it made improvements to network communication. We're going to start by looking at a simple system from some time ago. You won't see this before, and this is when computers were attached together through network cabling, typically using coaxial cable. And this was a system called 10^2. Now in this system they were all sharing one wire, and so what could happen was that two computers here could transmit at the same time. When this happened, we got what was called a collision on the wire from the two transmitting stations, and their signal would be interfered with. So each computer listened for collision. In fact, they had something called a system called collision detection. And they would stop transmitting. They would back off some random amount of time, and then they would start transmitting again. But before they transmitted, they always sensed the line to see if it was free. This system was known as carrier sense, multiple access with collision detection. And what we had here, there was a term called collision domain. And all these computers were in what was called the same collision domain, because a collision could occur between any of these computers if they both transmitted on the same at the same time. So enter the hub, which really operated the same way, but it changed from a linear structure to use a topology called a star. And one of the disadvantages of this older system here was that if you had any wiring error, it could take down all three computers in the whole network. So the improvement was the star topology, but a hub worked at the same OSI model. That is, it worked at the physical layer. And it's simply, if a packet came into a port here and it used twisted pairs instead of coax, it simply regenerated those electrical signals down all the other ports. Now we could still get what were called collisions, so that if this first PC generated a signal, a frame, and the third PC, then inside this hub we could get collisions that would occur at the same time. So this system also used carrier sense, multiple access with collision detection. This is part of the Ethernet standard, and if we have a hub, this is the system that has to be used. So whether we have this early topology or whether we have a hub, we had the same thing. Whenever we have collision detection, we can only operate in half duplex. Because we're always using a system which senses the line before we transmit, if there's anything on the line, we don't transmit. So we'll either transmit or we'll receive information, but we can't do both at the same time. As well, if we look at what is called the collision domain in a hub, the collision domain is the entire network that we have on our hub. It's all one collision domain. So this is very much like people talking in a room. You can either talk or you can listen. You typically can't do both at the same time, and if you try to do both, your information gets corrupted. And the advantage of using a hub style architecture at this time was that it was relatively cheap to purchase and implement. A hub, it used star technology or topology so that if you had a bad connection or wire, it didn't affect the other connections to the other computers, and so your network was still up and running, but you may have only had one PC that was down instead of taking down the whole network. So now enter a more elaborate device, and this device is called a switch. And how did a switch differ from a hub? Well, inside the switch, we had a whole CPU inside here. So we had a computer, we had memory. It also used a star configuration, and it had quite a bit of memory that were allocated to two buffers. So this is just memory. And inside these buffers, one would be the transmit buffer, one would be the receive buffer. It could store frames. So more expensive switches had more memory to store frames that were coming and going out of each of these ports. So that was one difference. So here we have memory for each of the ports. A switch also had a table inside. But what was different about a switch was that a switch actually did some processing on all the frames that passed through it. So rather than just simply electrically regenerate the signals, it actually looked at all the frames. And inside it had a big table where it kept track of every MAC address that it saw on all the ports that it had. So here we have a simple port number 1, port number 2, port number 3. Very easy to have ports, 48 ports on a hub. And we'll give these 3 PCs a MAC address, and we won't write all the 48 bits. We'll just use the last 8 bits, and we'll say this MAC address ends in A1, this ends in 03, and this would end in 23. So these are fairly random MAC addresses. Now let's suppose that PC1 here wants to send a frame to PC3. At the very beginning, when the switch is first turned on, all the buffers are empty. This big switch table is empty. And one of the first things that the switch does is, if it receives a frame, it looks in the switch table to see if it has an entry for it. So here, this is sending a frame to 3, so we would have as the destination would be 23 would be the destination MAC address in the frame, and the source address would be A1. So that frame would come up here, would get stored and processed in the transmit buffer. It's being transmitted, and the switch would try to find out what port should I send that to. Now, it's not in its switch table. So if it's not in its switch table, it will, it will flood that frame. and by flooding that frame, it sends the frame out all the ports. And that might seem a little inefficient, but it doesn't matter. This PC number 2 here will ignore the frame because the destination address is 23. It doesn't match its address, so it'll ignore it, but that will come down and get delivered into this PC. If it does have an entry, so eventually the switch is going to learn what MAC addresses, what machines are actually tied to what port. If it does have an entry, then it simply sends that information directly to the right port. So you cut down on traffic to directly to correct port. Now, how does it learn these addresses here on the port numbers? Well, we talked before about ARP packets, which need to get sent out. It actually, through reading frames and processing only some of the information in the frames, it can learn what addresses are on what ports. For instance, if a frame comes in from port 1, it simply needs to look at the source MAC address and would find, this MAC address is associated with port 1. And these come from ARP packets. They can come from any frames which are sent in and out of the switch ports. Now, switches tended to be quite expensive, and this is why at first hubs were used instead of switches. Computers have drastically reduced in price, especially these types of embedded computers, and so eventually they became quite cheap, and because their performance is typically better, they have replaced virtually all hubs, and you won't typically see hubs in service anymore. Now, switches have different performance characteristics depending on the level of technology inside the switches. Some switches are faster than others. So you may have, for instance, each of these switch ports may be capable of fast Ethernet, which is 100 megabits per second. But one item of the switch is how fast can it transfer information between its ports. So some switches may be able to do this at only 100 megabits per second. Some may do 200 megabits per second, and so on. Sometimes this is referred to how fast the backplane works, and the backplane is what these are all connected to. But really we're just looking at how fast that frames can be switched between the ports. Even though the ports work at 100 megabits per second, can I send data faster? And we'll look in a second why that is important. Take a second to look at the details of information being transmitted between a PC and between a switch port. In fast Ethernet, it's using 2 pairs to do this. There are 4 pairs in the wire. Information is being transmitted from the PC on one pair, and it's being received in the other. But because frames are being stored in this buffer here and being processed, we don't have the same system that we do in hubs. Signals aren't being regenerated inside the hub and colliding. So there is no, it's really important to note, there is no collision domain here. There's no possibility for collision, because between the PC and this port, it can transmit as fast as it wants, and all the frames simply get stored up in the transmit buffer. They don't go anywhere but the memory. And if information has come in the receive buffer, it's going to come down in these receive wires and can go directly to the PC. So there's no collision domain, and we can work in what is called full duplex mode. Now, just operating in full duplex can by itself double the data that's being transmitted between one PC and another on a switch if both are transmitting at the same time. And we'll look at an example here of a switch and 4 PCs. And let's suppose these 2 PCs here that I've drawn in red are having a video chat. Each one requires, the video chat to transmit requires 10 megabits per second, so the switch is capable of this in each of these ports. And let's suppose the green PCs are having a video chat between themselves. Now the beauty of a switch is that these two can transmit and receive 10 megabits per second each because we're working full duplex. And at the same time, these two could be transmitting, however, at 10 megabits per second. However, the switch inside has got to make sure that it can move 20 megabits per second full duplex in each direction. So in total, it would have to actually move 40 megabits per second at once. It would have to have that capability inside. So often most switches will move much more data inside between the ports, or have the capability than each of the ports need. But you can't do this in a hub. You certainly wouldn't have the bandwidth to be able to support it, because in a hub, even if you had 10 megabits per second channels, first of all, you would have in a hub only half duplex. And so you could only go 10 megabits per second in one direction. So you could get video one way, but the other person couldn't send the video at the same time to the other person. You certainly couldn't sustain 2 conversations at the same time. You maybe have a red conversation, but only the video going in one direction. And so this wouldn't be workable at all with a hub. And so you get much better performance in a switch than you would with a hub. And that's why switches have taken over. In some situations, whether this is a hub or whether it's a switch, you might not notice a big difference. For instance, let's suppose we have 4 PCs here, but most of the traffic in this company is between a PC and a server. And typically we're just downloading files. Maybe we're just reading, maybe this is an email server, maybe it's a file server, but we're typically just retrieving information from it, and it's going from one PC or another, and we don't have much communication between the PCs. In this case, whether we have a switch or a hub is not really going to give us a lot of difference, because we typically only have half duplex communication and we're only sending to one device. But as soon as we add maybe a second server off our switch, and as soon as maybe this is for mail and maybe these are for files, now all of a sudden we have these machines wanting to get information from both. So maybe this blue machine wants to get information from the mail server. Let's suppose these two are hitting the mail server quite often. And let's suppose the final 2 are hitting the file server quite often. Now the switch technology can really take an advantage of this. Another thing which tends to happen in switches is that you tend to have 1 or 2 ports which are much faster. So these, it's quite common for these many ports, or most of the ports, to be, say, fast Ethernet at 100 megabits per second, and have 1 or 2 ports which are at one level higher. for instance, gigabits, 1 gigabit per second. And so with one port quite a bit higher, we can support, even if we just have a single server, all these machines may be wanting to get information at 100 megabits per second, and this 1 gigabit per second can satisfy the 100 megabits per second for all these machines, for at least 10 machines, because it can transfer into the switch at a gigabit per second, so much data, 10 times more data per second than you can get from a channel, and so it can support 10 machines here. Another advantage of this fast port that you'll see on many switches, so let's suppose we have some fast Ethernet ports here, but we have 1 gigabit per second port here, and we have another switch with a gigabit per second port here, and then the fast Ethernet ports, is that these switches can be cascaded together, sometimes called an uplink port, and so this can now operate as one single switch. And you can certainly get information from one switch to another much faster because of the higher speed link here. So you often will see switches with 1 or 2 high-speed links here. Sometimes they work on copper at 1 gigabit per second. Sometimes these can be even higher speed links using fiber. Now switches do not have a MAC address in each of these ports because the ports are not the final destination for any frames that are sent through it. So you don't think of switches or these switch ports as having MAC addresses or IP addresses. However, there are types of switches which are called managed switches. So you can buy unmanaged switches which are relatively cheap, anywhere from sometimes $10 up to $100 depending on the speed. But managed switches have a more extensive CPU and computer inside. And a managed switch often will have a special other port on it. Here's my switch. Sometimes it's on the back, or often it's on the back. I'll show it here. But often we'll have a serial port on it, sometimes USB. It's called a console port. And you would attach a cable to a serial line on a computer. So this could be, this port here can be a number of different standards, and the older standard is a serial called RS-232. Today they use USB as a way to communicate. But through the console port, you can hook up a computer and you can use a command line interface to send commands to the switch, and you can do things like configure special features on the port. You can gather statistics on how much data is flowing in and out of the ports. You can set special access control lists to maybe filter out what computers can actually use the switch. So it's a way of providing security. There are other features that we'll study later in the course called VPNs. And so these are managed switches. They are much more expensive. And when you have a managed switch, you do have information which is destined for the port, because you can configure it not only through the console port, but even if you have a computer on one of its ports, you can connect through some Ethernet or network communication standards called Telnet. And if Telnet is a non-encrypted standard, basically just acts as a terminal to give you this command line interface, or a secure shell, and you can send frames directly into this command line environment part that's provided by the computer inside here. In this case, there is an internal MAC address and usually an IP address that this switch will respond to provide this interface. So that's called a managed switch, and in our course we're certainly going to use managed switches. The most two common are Dell and Cisco. The Packet Tracer supports a simulation of the Cisco switches. However, Packet Tracer does not support all commands that Cisco switches can use. Dell's are certainly much cheaper, and many organizations that maybe don't want to spend quite as much money will use Dell switches, which use a command line interface which is very similar to Cisco but can't be identical. And there are HP switches and other companies that make managed switches as well. Last thing we'll talk about on switches is what happens with broadcasts. If a frame is sent by PC1, and usually ARP will send layer 2 broadcasts, but a broadcast is any frame which has a destination MAC address that is all ones. So the MAC address is FF:FF, FF, and so on. Well, what a switch does with this is it will flood, because there's no one machine that should go to. It floods that frame out every port. And so although in a switch there is no collision domain, the broadcast domain is the entire amount of computers here that are attached to the switch. So any broadcast is sent to all this. So there's no limiting of the broadcast domain with the way that a basic switch works. So a basic switch has a single broadcast domain. Now the final questions to pass in and to answer for this is, how does a switch differ from a hub? And so what I'm looking here is for you to write something in your own words. I don't want you to cut and paste or do any more research. You should be able to get it just from this video, but try to put it in your own words, and sometimes by putting it in your own words it tends to consolidate the information a little more. In the second example here, I've got a device, a 4-port device, and what we're trying to set up here is I'm trying to have a video chat between machines 1 and 4 and a different video chat between machines 2 and 3. The video chat requires 75 megabits per second for video audio sent in one direction. So that's requirements of the codec and the webcam that we're using inside these machines. So what device would I need to buy and why? And I want the cheapest device that I can get away with. So can this simply be a hub if all the ports here are 100 megabits per second? Can it be a $200 switch if the ports are 100 megabits per second, and internally this switch can transfer data at 100 megabits per second? So it can just move data from one point to the other, but it can only move it at a rate of 100 megabits per second. The third option is a $500 switch, which can move 200 megabits per second internally. Each of the ports are still fast Ethernet at 100 megabits per second. The $700 machine internally, the difference here is that it can move data internally 500 megabits per second, but make sure you use the cheapest switch possible. And maybe you might need the $800 switch, which each port can work at gigabit per second. And also internally it can move data at a gigabit per second between ports. So you need to choose which device to use, but more importantly, the points are going to be based on why did you choose that.